Baik, Assalamualaikum and good morning. This is part 3 of my lecture on coastal depositional environments. And today we will look at the next type of marine process, which is tidal processes. Now, if you've been following the lectures for the past few weeks, you know that we've been looking at coastal depositional environments, and the coastal depositional environment is a complex system where you have interaction between alluvial physical processes and also marine processes. And in the previous lecture, we looked at one type of marine process, which are waves, and today we look at tides. So what are tides? Tides, or in Malay, air pasang surut. This is any periodic fluctuation in the water level that is generated by the deformation of the ocean surface by the gravitational attraction of the moon and the sun. And the main point here is the main point here is periodic. You have regularly repeating changes in the sea level. And these alternatives between high and low sea level occur at daily scales, monthly scales, annual scales, and even longer scales. These are classical. This is a classical example of how tides work. So this is the same area along the coast. You can still see the same boat, the same docks on the side here, right? So during one part of the day, you see that the water level is very high, and the boat can actually float on the sea. But later during the day, water level can go down, and now the shoreline is very far away, right? So this high water level is called high tide, and when the water level is at its maximum low, is called the low tide, air pasang and air surut. Okay? And the rise and fall of tides happens daily in this area at regular time intervals, which is very important. The tides are very regular, that you can actually predict when it's going to happen in the future. Right? Most parts of the world is 2 tides per day. So there's going to be one tide roughly around every 12 hours. So you come back, you have the next day after 12 hours. If we started with high tide, we're going to get another high tide after 12 hours. So the water level fluctuates at regular intervals, and this fluctuation can be expressed as a sinusoidal wave. Right? So you have this graph here. This is tidal amplitude. This is positive amplitude. This is negative amplitude of the wave, and versus time. We're moving through time here. Right? So there'll be fluctuations from high tide to low tide, and the cycle continues back to high tide and low tide, and so on. Right? Following a certain period. Okay. So because of this, you get this vertical movement of water going downwards to low tide, and then it also goes upward again. Now the movement is not just vertical. Tidak hanya naik turun saja. It's not just vertical up and down because of you have a coastline which is becoming shallower and shallower towards the land. You also get a lateral component to movement of your tides, right? So let's say you start with time 1 here. This time 1 on the wave. This is time 1, the cross section. This is your coast, right? And this is your water. Right? And during time 1, it is high tide. Okay, your water level is up to here. But then you get to time 2 when the water goes down. Right? And this is low tide, right? So what happens also is that you get a current moving from land to the sea. You know, the shoreline is moving seaward from here to here, and water is also moving laterally because of this. And this current is called the ebb current. It is the seaward current from high to low tide. right? Then you reach low tide during time 2, which is here. Now after a certain regular period, it wants to go back up again, right? So the water level rises and rises until it reaches the maximum, and then you get to the high tide level. And once again, you get also a lateral movement in the water and a change in a shift in shoreline landward, and this is called the flood current. Okay, so this single cycle from ebb to flood again back to high tide is called a tidal cycle. That's one cycle of tides, right? And during that time, you have an ebb, a seaward current from high to low tide, and a flood, a landward current from low to high tide. Now, you have a level which is low tide, and then you have a level which is high tide. And that vertical distance between the two is called the tidal range. So that's an important term you need to know. We'll come back to that in the next lecture on the different environments in the coastal system. Okay, so you get regular fluctuations in water level, right? And these are called tides, and they occur daily. I can actually predict when it's going to happen next day or even next week, right? Uh, but now let's ask the question: why do we have them? Why do we get tides on this planet? So we need to explain uh, the physical process behind tides and what is operating them. And we can explain them by two models, actually two models to explain. One is called the equilibrium model, and the second is the dynamic model of tides. So we go one by one, go to the first type first, the first model, the equilibrium model. Okay, so what is the equilibrium model of tides? It is a simple model relative to the dynamic model. It is a simple explanation of how tides are formed. And it makes some simple assumptions about in order to make us easily understand how tides are formed, right? So first we make the assumption that we are dealing with a perfect sphere for the earth, right? And there is a single ocean covering the whole earth. We know this is not true, right? We have lots of oceans separated by continents, but we need to make these simple assumptions first. We have a single ocean covering the whole earth, and this ocean is of uniform depth across around the globe. Tell you that the surface, the seafloor is smooth. Okay? There are no continents, and the oceans respond instantly to tidal forces, meaning that the water just moves instantly. You have gravity is pulling it, so you just instantaneously get one bulge building up. Doesn't take time to build up all that mass, right? But that's not the case. But let's stick with this first. This equilibrium model. So a single ocean covering the whole Earth, ocean of uniform depth, no continents, and the ocean responds instantly to any forces. Now, the main players in this in tidal forces are the sun, the moon, and the earth, and you have gravitational pull between them, and you also have them moving around each other, right? So the sun and moon play a role in generating tides, but in this model, we let's ignore the sun. The sun might be larger, but the moon is more influential, even though it is smaller, because it is very close to the Earth. The moon exerts about 70% of the tidal force on the Earth. So in this simple model, you have a uniform body of water, the ocean here, colored in blue, right? That is the Earth, that is the moon. This is representing the revolution of the orbit of the moon around the Earth. And this is the common center of mass between the Earth and the moon. Okay, the axis in which you have the two bodies here dancing around each other. I'll show you an animation later. Right? And remember also that the Earth is also rotating in the same direction. So almost everywhere in this simple model, the ocean rises and falls twice a day. Okay, so we have two tides per day in this model. The two sets of tides are the result of two oceanic bulges on one on either side of the globe. So you have this body of water, and notice I drew it here not as a not as a perfect circle, but you have these thicker parts on the left and the right here, right? So these are the two tidal bulges where the water is deeper, okay? And the Earth rotates, and any position on the Earth will pass between these two bulges. And this is your high tide level. Then if the location moves to in this point, this is your low tide level, where you have a thinner body of water. Now, just also remember in this drawing, our plane of view, this is the North Pole. Okay, you're looking at the axis of the Earth in this case. Okay, from the way you look at it from above. Now, the bulges are caused by two forces. First, you have the gravitational attraction of the moon. The moon is pulling all that mass from the Earth towards the center. And then you have centrifugal force caused by revolution of the Earth-Moon system about its common center of mass. Let's look at this in detail. So you have the Earth and the Moon revolving around each other around a common center of mass, which is roughly around here. Yeah, moving around each other, and also the Earth is rotating in the same direction. Now let's say we are able to pause this movement for a while. Let's pause it. Stop everything. That's possible. So you have the Earth here, which is larger, and then you have the moon, right? And you have gravitational attraction of the moon, and this is strongest on the side facing the moon. It is also pulling the body water on this other side, but it's strongest here because it is nearer, right? With the cap. So because of a gravitational pull here, water rushes to this point to form a bulge on this side. A bulge of ocean water is produced on the side facing the moon as water is pulled towards the moon. And you get a high tide on the side, right? And very thin layer of water on the other side. Remember, this view is from above. That is the axis of rotation of the Earth. Okay, but the Earth and the Moon are not static, right? So they move around each other around a common center of mass. That is common center of mass marked as a cross. Okay, so the Moon is orbiting in this direction, and the Earth is also moving and dancing. They are dancing together, basically, right? The Earth and the Moon both revolve around the common center of gravity. This is a point located within the Earth, about 1,700 kilometers from the surface, and that is about a quarter distance to the center of the Earth. Okay. So the Earth's motion around the common center of gravity causes matter in and on the Earth, including its oceans, to move outward now. Okay, so these are dancing around each other, right? So you have gravitational pull on this side, but you also start to get centrifugal force on the other side because of the revolution of the Earth's moon system. So this red arrow here represents gravitational pull. This dark blue arrow represents centrifugal force, which is operating in the opposite direction. Okay, so the moon's gravity on the near side of the Earth, on this side, right? It is strong enough to overcome the outward moving centrifugal force on this side, gravity is stronger than centrifugal force. Okay, so I draw it with a bigger arrow here. And this represents centrifugal force. Okay. But on the other side of the Earth is far enough away from the moon that centrifugal force is stronger compared to gravity. So you get two opposing bulges on either side. Okay, and these bulges represent your high tides, and these areas at an angle to your bulges here are your low tides. Okay? Okay, so we all know a single 360-degree rotation of the Earth on its axis takes 24 hours. Right? That's a day on our planet. Now, let's say you have a point on the Earth, a position on the Earth. Right? I am drawing here a house on stilts. And at this point, the house on stilts is at is just above the water level, right? Let's say the time is 0 hours here, and during this time it is high tide because it is inside the bulge. Okay. Now, after 6 hours, the Earth rotates, and your house is now here. It is not at the bulge; it is in shallow water. This is low tide, right? This is 90 degrees to your bulge here. And after 12 hours, it gets into another bulge, and it is now again high tide. And then it goes back to a low tide after 18 hours, and then it continues to complete a circle after 24 hours, gets back to the first high tide. Okay, so you get 2 tides per day. Okay? A point on Earth will pass through a bulge, a tidal bulge, every 12 hours. These are high tides. And so a point on Earth will pass through 2 bulges every 24 hours. So it means you get 2 tides per day in the equilibrium model. And this occurs every day and should be predictable. So you get 2 tides per day, 2 tides every 24 hours. So it means that you get 2 high tides and also 2 low tides per day. And this kind of tidal cycle with a period of 12 hours is called a semi-diurnal tide. So this is a semi-diurnal tide. So ideally, you should get 2 tides per day because of the rotation of the Earth around going through 2 tidal bulges caused by gravitational attraction with the Moon and also opposing centrifugal force caused by the revolution of the Earth-Moon system. Okay, so get whole circle 360 degrees after 24 hours, but that's too simple a story. You need to remember the moon is also moving. It's not stationary. It is also orbiting around the Earth in the same direction. Okay. So after 24 hours, this house here will have reached the 360 degrees again. At 360 degrees, comes back to the same position, right? But the moon has also shifted a little bit in the same direction. The position of the tidal bulge will have shifted after a 360-degree rotation of the Earth. Has moved a little bit here. So if you want to catch up again to the tidal bulge, it's going to take an extra 50 minutes. Dia tambah masa sikit in order for this position here, the rotation of the Earth to catch up with the movement of the Moon. Okay, so it's not exactly 24 hours. It actually takes 24 hours and 50 minutes to pass through 2 times because the bulge has moved because the moon has moved. So a single tidal cycle, one tide, occurs every 12 hours and 25 minutes. So you have tides operating at a period of 12.42 hours, right? 12 hours and 25 minutes. So it can be expressed as waves here. So you have time in days, and then you have your amplitude, positive and negative. So you should have two tides per day in semi-diurnal tides. Okay? So you notice these two peaks here, single day, two peaks, and so on. Right? And you can make a graph for long periods of time here, and you can actually predict when the tide is going to happen in the future. Okay? So just to have a look, just to have a more detailed look here. So uh, you have a flood tide where your tides are rising until it reaches the high tide, and then you have an ebb tide, falling water until it reaches the low tide. And the cycle continues on and on again. And a single ebb flood tidal cycle, flood cycle is called a tidal cycle because every 12.42 hours. So it should be two tides per day, and you have a tidal cycle every 12 hours and 25 minutes. So okay, we understand tides now, but that is an ideal model. That is a simple model, but we live in a universe which is complex. Tides are actually very complicated. They're actually different periodicities. You get in reality, you actually get lots of different kinds of tidal cycles, and they are operating at different periods. Okay, and these different tidal cycles we call them tidal constituents. And they are caused by different kinds of interactions between the Earth, Moon, and the Sun. Okay? There are lots of different tidal constituents. If I remember well, there might be more than 100 types of constituents with different periods and controlled by different kinds of factors. Okay? So I'll just show you some of the common examples below. So we looked at the simple semi-diurnal tidal cycle. It has a period of 12.42 hours, right? And it is caused because the Earth rotates, and then because you have the Moon and Earth revolving around each other. So you get gravitational attraction, and you get centrifugal force in opposite direction, and you get the two tides per day. But you can also get diurnal tides, and the period is 24 hours. It is caused by Earth rotation around an inclined axis. You can also get monthly tidal cycles with a cycle period of 14.77 days, so-called mid-spring cycles, and they occur because of interaction between the sun, the moon, and the earth. You can also even have annual cycles with a tidal cycle completing every 182.6 days, and that is caused by a sun-moon declination. So you get different kinds of tidal cycles, right? So they have their different periods, but they are actually interacting with each other. You get different kinds of tidal cycles superimposed on each other, right? So if you remember, you know about wave theory in physics, right? If you have two waves, right, they're different periods, different frequencies, they can actually sometimes cancel if they are in phase or out of phase, right? Can actually cancel each other, or they can amplify each other, right? So this is what happens also with tides. Okay, so you can have different periodicities which are superimposed on each other and which can dampen some tidal signals, cancel out some tidal signals, or even amplify tidal signals. So just show you two common tidal constituents. Uh, First, you have diurnal tides. In some parts of the world, you can actually get just one tide per day, not two tides. And this is because of the declination of the moon as it orbits the Earth. So you have the Earth here, And then you have the moon here, right? And notice our plane of view is now from the side, okay? And the axis of rotation is here. It's not the same viewpoint as before, right? So you have the two tidal bulges, right? But in this case, notice the position of the moon here. It is orbiting at an angle. In this case, 28.5 degrees inclination. Okay. So because of this, you get an inclined orientation of the tidal bulge also. This plane of view, this tidal bulge here is higher, right? Compared to this side. It's not parallel to the equator. Remember in this case. So in some parts of the world, let's say position here on the red line here, as you rotate the Earth, some points can just pass through only one bulge here, this high tide bulge. On this side, not so much. Right? So you just get a feel of this bulge. So one tide per day just passes on one tidal bulge. Okay, so it experiences diurnal tides, one tide every 24 hours. So now let's look at another example of a tidal constituent. Now, this is a monthly tidal cycle now. You have neap spring tidal cycles. Okay, so you have the Earth here, it's rotating. So you're looking at it from above, that's the axis, okay, from above. And then you have the moon, which is revolving, dancing around the Earth in the same direction. And now you have the sun playing an important role, the sun here, right? So sometime, okay, the moon takes 1 month to move around the Earth, to orbit around the Earth. One moon. So in Malay, it is 1 bulan. Right? Okay. So as it moves around the Earth, it takes 28 days. Okay, that's 1 month. And so during certain times, you get the moon having a position like this. Uh, the moon, the sun, the Earth lie in a straight line. Okay, at this time. And because of a combined gravitational pull of the sun and the moon, you get greater average tidal ranges, high tides during this time. And so these are called spring tides. It occurs 2 times per month. Okay, so that's a spring tide. After 14 days moving around, you get another spring tide. But now the moon is on the other side. So you have the sun here, the earth here, and the moon on the other side. So you get a spring tide during a new moon, okay, as the anak bulan. And you also get a spring tide after 14 days when during a full moon, as bulan mengambang. You also get times where the moon and the sun are at right angles, 90 degrees to each other relative to the earth. They are exerting, okay, you have gravitational pull in opposite directions, so you get a smaller tidal range on these sides here. Right? So during the 7th day and also the 21st day, you get a half moon, and during this time, you get small tidal ranges. So these are your neap tides, very low tides during this time. Okay. So these are called neap spring cycles. Okay, so you can express it again as waves. So in this case, you have times in days, that's a single month, and then you have water height in meters. And see what happens. First, you get the daily tidal cycles. So, if it's semi-diurnal, you get the 2 tides per day here, right? High tide, low tide, high tide, low tide, and so on. So zigzagging like that. But then you also have a neap spring tidal cycle, and it is superimposed onto these daily cycles. So what you get is these bunches of tidal cycles where they are very high at this here, and bunches of tidal cycles which are very low tides here. very narrow tidal range, and a wider tidal range. Okay? So this forms another wave superimposed onto the daily tide cycles. And this is the mid-spring cycle. Okay? So going from one spring tide to the other spring tide, if it is if you are having semi-diurnal tides, 2 tides per day on your coast, this occurs every 14.77 days, and you get 28 ebb flood tidal cycles. Okay, so but if you only have one tide per day, because you have diurnal tides, so you only get because every 13.66 days, you only get 14 ebb flood tidal cycles, half of that. Okay, so remember that you get two superimposed waves here, right? The daily tidal cycles and then the monthly cycle here. And this is during very high tides, and during the months in the month you get these times where the tides are very high, and another times of the month you get tides which are very low. Okay? Yeah, this is air pasang tinggi. These are spring tides. Sometimes you hear about periods of very high tides uh, in the news, right? And that is commonly associated with spring tides because of interaction between the Earth, Moon, and the Sun. So that is the simple story, the equilibrium model of tides. Let's look at the second model explaining tides. This is the dynamic model of tides. Um, the equilibrium model is very useful when you want to teach the concept of tides and how the moon and sun interacts with the earth, so on. But if you want to actually predict tides, you need a more complicated model, which needs to look at the interactions between the different tidal constituents, whether they cancel out or whether they amplify each other, right? Because there are too many tidal constituents interacting with each other. You need to know the sum of it all. And how they interact, what is the total tidal influence on the coast. That's one way to explain it. So the equilibrium model is too simple. It cannot predict actual tides because it is based on a simple model with a global ocean. Right? But in reality, on this planet, you actually have more than one ocean. There are many separate oceans, and they are unequal depth. Some are deeper, some are shallower, right? And these oceans are separated by continents now with varied geometry. And there's also complications caused by the Coriolis effect because the Earth is rotating. And the oceans are made of water, which is fluid. And they do not, when you have gravitational pull, it does not react instantaneously as a single uniform body, right? It responds slowly to tidal forces because of its large mass, because of the extremely large volume, and also the wide area. So, in reality, you don't get two large bulges on opposite sides of the Earth. You still get the interaction between the different celestial bodies, though. You still get a centrifugal force and gravitational pull, but you don't get nice, perfect two large bulges on opposite sides of the Earth. Okay? But what you get are tides which are moving as giant waves. This is the shallow water waves. They're so large that everything is now above wave base. Okay, so they move as giant shallow water waves, and the water moves in large circles and rotate around these points, which are called amphidromic points. So these are amphidromic points here, and these circles here with an arrow shows you the direction of rotation of these large waves. So we have what is called amphidromic circulation. And this is because you have geography now. You have landforms in between. You have a shallow water body, large mass of water here, and the system is now more complex. So let's have a closer look at amphidromic circulation. Let's take the example here of the North Sea. This is a classical example on all of the textbooks. This is from Professor Dalrymple's book here, 1992. So these are your land masses. You have the United Kingdom here, and this is Europe. That's Norway. Okay, and this is the North Sea, colored in white. Okay, so in the North Sea you have semi-diurnal tides, 2 tides per day. Okay, and you have, in this case, 3 amphidromic points, and water is moving in circles around these 3 points. So on this map, first you have this fixed solid arrow line here, and this shows you the direction of rotation of your amphidromic tidal circulation. Okay? Here, all these are counter-clockwise, large counter-clockwise rotation of tides around amphidromic points. So your black dots here are your amphidromic points. And also you have co-tidal lines. These are time of high water. So example, you start here. This is time during 0 hour. After 1 hour, high tide reaches here. 2 hours reaches here. 3 hours here. 4 and so on. So it moves in a circle, right? Tells you during what time of the day where the high tide will be. And then you also have co-range lines here. These are lines of equal tidal range. So your tidal range here will be 3 meters, 2 meters here, 4, 3, 2, right? It's getting shallower and shallower. And then 1 meter here gets shallower until you reach the amphidromic point. So if you make a cross section, I'm going to take this circle here as an example. If I make a cross section here, right, this is how the water level will be. Let's say I am 7, 8, 9. I am here during time 10. So 10 hours. After 10 hours, my high tide will be on this coast here. Right? Tides will rise up to 2 meters. It's on the tidal line here. This time. So if I make a cross section from west to east, this is how it roughly will look like. Right? This is the piece of land masses here, the sea bottom, and this is your water body. I will get a high tide on this side, on the western side. But then when I go towards, if I go towards the amphidromic point in the middle, the tidal range becomes smaller and smaller and smaller. And when I go to the opposite side, let's say I'm on time 10 here, on the opposite side is going to be hour 5, previously 5 hours before, right, for the high tide. But right now, during time 10, there's not going to be a high tide. You get a low tide on the other side. Okay. And after several hours, this will change again. This part will be low tide, and this side will be high tide. You get this sloshing around of water on both sides. These are actually standing waves. High tide oscillating with low tide, and at opposite sides. Okay. So you get vertical movement of water, sides here, which can also be transformed to a lateral movement of water, your tidal currents. Okay. So you get counterclockwise rotation of tides around amphidromic points. So in reality, this is how tides move in 24 hours. Okay, so the lighter colored parts here are your high tides, and the darker colored parts here are your low tides. So lighter is high, the darker parts is low tides, right? So notice the high tide changes its position in 24 hours. So in this case, this is a semi-diurnal tidal constituent, right? You have tidal rotation of M2 semi-diurnal tidal constituents, which has a period of 12 hours and 25 minutes. Start here, 0 hour, high tide moves around, comes back to the same position at 12 hours and 25 minutes. Okay? And you get circulations which are in some places it is clockwise, some places it is counterclockwise. Okay? These large bodies are moving, and these are standing waves, and that is why you get tides. It's not just a simple two bulge tidal system, you get lots of bulges, and the bulges are moving in a circular manner. Okay, so that's the first part of this lecture. We looked at the forces which play roles in the development of tides, right? So you get high tides and low tides and tidal currents. So those, but let's look at the geological expression. What are the resultant facies that can be developed because of tides? So going back to sedimentology now, sediment transport and deposition in tidal environments are characterized by these four things. First, you will get current generated bed forms, just like in a river. Right? So depending on the flow velocity and the grain size, you can get plain beds, you can get ripples, you can get dune bed forms. Right? You also get suspended load during low energy intervals between the tides. These are slack water periods. Right? So you get suspension fallout. But you now also have a regular rhythmic deposition because of tidal periodicity. 2 times per day, you can get regular alternating fashions. And you also get periodic current reversals due to ebb flood cycles. This is the main different character. This is this is very different from a river, right? A river will flow from the land to the sea, so you get unidirectional current. But in a tidal environment, during one part of the day, you get one current moving towards the sea, and another part of the day, the current will move in the opposite direction from the sea to the land. You get current reversals, and the current reversals are periodic. There's a regular cycle to that because of ebb flood cyclicity. So the first type of tidal facies, we'll be looking at what we call rhythmites. These are interlayered sand mud beds, and the interlayering is rhythmic. They form nice regular stripe patterns. Okay, so let's try to build rhythmite from scratch. So let's say you have waters of this depth on a shallow coast, right? Um, so in this case, you have a high energy ebb current moving from the land to the sea. Land is on the left here, sea is towards the right. Okay, so you have an ebb current moving here. So your water is actually moving downwards from high tide, even though it's getting shallow and shallow. Okay, so because you have an ebb current here, it is high energy. The only grains that fall down are coarser. So you get suspended sand fallout, marked by yellow here. So sand particles will start to fall down and then develop a bed of sand on the seafloor. Nice bed of sand here. Right? That is during the high energy ebb current. So let's say in the semi-diurnal tidal cycle, after 12, roughly 12 hours, you reach the low tide now, after an ebb current. And once it reaches the low tide, there is no longer movement. Okay? The water becomes tranquil and quiet. Okay? And this is what we call a slack water period, the quiet periods in between ebb and flood cycle, ebb and flood currents. Okay? Air dia tenang maksudnya. Okay, so there is no movement. So now it is low energy. The velocity is low enough that any particles in suspension, most of the time it is mud, clay, and silt, will start to fall out from suspension, will fall down and lay a mud bed here. And this mud layer we call a mud drape. It is draping, it is covering the sand layer below. Okay, so mud is deposited from suspension during low energy slack water periods in between tides. So how long does it take? Does this take? It varies. In some places, the slack water period can be several hours or 1 meter, several hours or 1 hour in duration. Right. Then after the slack water period, the water starts to rise again, and you get a current moving in the opposite direction from the sea to the land. This is the flood current. Now it is higher energy again, and the only so you start to get transport of sand, and then deposition of sand from suspension, and you get another layer being deposited at the bottom. Okay? So the sand layers are deposited during high energy flood currents while the mud stays in suspension. Okay, and then once it reaches the high tide, you get another slack water period, and you get another layer of mud being deposited. So in a single ebb and flood tidal cycle, you get this kind of layering, two sands and two mud drifts in between. And that is one tidal cycle. This one represents transport and deposition during the ebb. This one represents transport and deposition during the flood. And these represent slack water periods in between ebb and flood. So that's one tidal cycle. Now, cycles repeat themselves daily, right? So you get lots and lots of cycles, and they can, if you have a stable enough basin, and nothing much is happening in terms of tectonics, not much in terms of storms, and it's just tides operating in your coast, on your coast, you can get a very thick succession of lots and lots of tidal cycle, these sand mud packages here. They might represent tidal cycles for years or decades or centuries, ideally, right? So these are what we call tidal rhythmites. Rhythmic sand mud interlayering, and they are produced by periodic tides. So yeah, you can express the tidal cyclicity in the form of a wave again. In this direction it is up, in this direction it is flood, right? So you have tidal cycles every 12.42 hours here. So you get layers of sand forming during high and low tide, and slack water mud drifts in between. Okay, so just to show you an example, this is a modern day example. This is along a riverbank, and the riverbank is strongly influenced by tides. It's in Korea here, and these guys have made a trench, and notice the stripy layering. You get thin layers of sand, which is the lighter colored part, with mud in between the darker colored stripes here. And it's very rhythmic. They are roughly of equal thickness, right? So it's very regular. And when you start to look at this, you start to think, hey, these are tidal deposits. These are tidal rhythmites. Okay. From the ancient rock record, these are Precambrian age rocks. You get the same kind of regular stripy patterns to your rocks. Right? Darker colored, finer grain, lighter colored, coarser grain in this case. So these are interpreted as tidal rhythmites. Closer to home, this is a core taken from the subsurface several kilometers underground from offshore Sarawak. These are Miocene in age. Notice again, you get stripy layering, relatively irregular, right? So sands marking ebb or floods, deposition and transport, and you have mud drapes in between representing your slack water period deposition. So yeah, another example of a tidal rhythmite. This is also from Malaysia. These are Miocene age, and these are from the island of Labuan. Okay, notice the stripy layers here: sand, mud, sand, mud, sand, mud. These are tidal rhythmites. So if you have a thick enough and relatively well preserved succession of tidal rhythmites, you can actually identify deposition by different tidal constituents with different periods, right? Different tidal periods. So, for example, here, this is from the Precambrian in Australia. This person has interpreted these alternations between thicker stripes and thinner, very thin stripes in between here to represent neap spring cycles, with the thicker layers here representing spring tide deposition, the thinner layer, darker layers here representing neap tide deposition. So how does this work? Yeah? Different tidal periods can be recorded by vertical patterns in bag thickness and grain size. So make a sedimentary log here, grain size versus thickness. If you have neap spring cyclicity, during this is spring tides, higher tidal range, right? So higher tides, stronger currents, you can get coarser grains and also thicker beds. So you get coarser grains in this case, and also the beds are also thicker and they are much sandier. Okay, and during neap tides you get thinner beds because it is lower tidal range, lower energy currents. So you get finer grains, thinner layers, and a muddier succession. So you get these alternating thick, thin packages of sand and mud beds. And you might, in very very well preserved successions, you might even be able to count the individual sand mud couplets, and they should correspond to deep spring tidal cycles. So you might get alternating thick thin packages of sand mud pairs, which correspond to the one deep spring cycle 14.77 days. Right. So if you have a semi-diurnal system 2 times per day, you can get 28 to 29 sand mud pairs preserved. Or if it is diurnal, you get 14 to 15 sand mud pairs, and then you get the thick thin alternating packages. Now, the next type of tidal facies that we will be talking about are what we call tidal heterolithic beds. Okay, so these are thick successions of regularly interlayered, rippled sand and mud drifts. So the process of development is very similar to tidal rhythmites. Okay, so during the flood and the ebb current, you get development of a sand layer. But in this case, the sand layers have bed forms in the shape of cross-laminated ripples, and the ripples are directed in opposing directions, right? Because the flood and the ebb currents are in opposing directions, right? So you start with a flood current, let's say, so you get ripples uh, with cross-lamination dipping towards the right here. Then you have a slack water period resulting in mud deposition on top of the ripples, followed by an ebb current transporting and depositing another layer of rippled sands at the top here, but now oriented in the opposite direction, towards the left. The cycle continues on and on and on. You get interlayering between sand and mud, with the sand forming ripple shapes and also having ripple cross lamination. Okay. So in this case, they develop because your tidal currents are strong and fast enough to develop ripples. It's not just fallout from suspension, you actually get tractional currents. Now, tidal heterolithic bedding can be divided into three types. First, you have lenticular bedding, where you get thin, isolated lenses of sand ripples here, marked in white, enveloped in thick mudstone drapes, colored black, solid black. Or you can have wavy bedding. You have continuous but thin layers of sand separated by mud drapes of roughly equal thickness, equal sama tebal. Or you can have flazer bedding, where it is sand dominated, but lenses of mud drapes in between, which are not connected to each other. Right? Now, why do you get different types of heterolithic bedding? It depends on the concentration of suspended mud in the water and also the strength of the current. Okay. So if you have a coastal system and there is a lot of mud in suspension, and during slack water periods, all this mud in suspension will fall down to form thick layers of mud in between the sand, right? So you will tend to get lenticular bedding. Um, if you have lower suspended mud concentration in your water column, you might get wavy beds or really sandy systems where not much mud is in the system. You get flazer beds, and where you have a system where there is no mud, you just get lots of sand with cross beds and cross laminations. So it's not tidal heterolytic. Okay, so it is also controlled by current strength. Yeah? Higher energies, so you tend to get flazer bedding or wavy bedding. Lower energies, you get lenticular bedding. So you go from lenticular bedding to wavy bedding and flazer bedding, and you go from thinner sands and thicker muds to thicker sands and thinner muds. Okay. So you can get regular interlayering between ripple sand layers and mud drifts in between. Those are heterolytic beds. But when you look at heterolytic beds, it's hard to recognize a tidal signal. You cannot really see nice, nice cyclistics like leaf spring inside your heteroliths. It's a little bit chaotic. Not it's not well. It's very nice, perfect preservation of all the individual tidal cycles. There's erosion, there's periods of non-deposition in between, there's gaps in the record. So just remember, you can have heterolytic bedding, and and it is not actually diagnostic of tidal deposits because other processes can also form heterolytic bedding. You've already looked at fluvial overbank deposits like channel levees, right? And they can form the same kind of facies, interlayering of sand and mud. And later on, when we go into deep water facies, notice that you can also get heteroliths deposited in these kinds of settings. So to interpret whether the heteroliths are tidal in origin or not, you need to look at lots of different factors, right? It is likely tidal if you form a very thick succession, right? Because like if overbank floods, they don't occur regularly every day, so they form very thin intervals in between other kinds of facies, right? And whether or not there is evidence of cyclicity. Maybe some parts show thick alternations and so on. And then you need also to look at other kinds of evidence. Maybe we'll talk about that later on during the next part of the lecture. Okay, so just to show you examples of tidal heterolytic beds, these are flazer beds in the Miocene of Bintulu, Sarawak. And these are wavy, yeah, and lenticular beds, also from Sarawak and Bintulu. Now, this is a nice picture. This is also from Sarawak, but this is in the Biri area. This is part of the Miocene Lambi Formation. And you notice you get these lenticular bands with thick mud drips, which are the darker parts. You also get wavy beds in between. And these have been interpreted as tidally influenced deposits. Another example now from subsurface core several kilometers underground, where we penetrated rocks which are Miocene in age offshore Sarawak, and you get the same kind of fashions, interlayering between sand and mud. Some of them are wavy beds, some of them flazer beds, some of them are lenticular beds. When you see these kinds of facies forming very thick successions, you start to think maybe they were developed by tides. So let's look at another type of tidal facies. These are tidal bundles associated with dunes. Now we have currents and in a tidal setting, and if the velocity is high enough and you get grains of sand of a certain size, you can start to develop dunes, right? And the way that they grow is similar to alluvial dunes. Okay, so you have bed load, you have suspended load, right? And you get grain saltating, accumulating, and then once it reaches the brink, it avalanches down to form a lee surface. It falls down on the lee, along the lee surface and forms one layer, which is the crossbed faucet. And that layer can continue towards the trough in front of the dune to form a horizontal layer, which is called the bottom set or toe set. So you can actually, in the case of tidal dunes, you can get individual couplets of sand and mud layers being deposited in single tidal cycles. Okay, and these couplets actually form the crossbed faucets and bottom sets. So let's say I'm a longer coast where it is experiencing semi-diurnal tides, okay, but my tides are asymmetrical. Okay, so I have two tides here. So there's one tidal current moving towards the right, and that is stronger compared to the other tidal current moving towards the left. So the stronger current, I call it the dominant current, and the weaker current, I call it the subordinate current. So this might represent flood tide, and this might represent ebb tide. Doesn't have to be. It might even be the opposite, right? So this might be ebb or flood. Okay? But we don't know in this case. Just stick with dominant and subordinate. So let's see how tidal bundles are formed. You have a dune. During the strong dominant current, you get a sandy foreset and bottom set being deposited. You even get ripple cross-lamination developing on the bottom set. So after some time, you reach the slack water period, you get a mud drape on top of your sand layer. And after the slack water period, you get the subordinate current moving in the opposite direction. You get another sand layer being deposited on top of your mud drape, and then another slack water period, right? And you get deposition from a single tidal cycle. Very similar to tidal rhythmites and tidal heteroliths. It's just that in this case, your layers form associated with crossbeds. Okay. So these sand mud couplets in crossbed faucets, and they are developed by the same flood cycle. So you get these things that we call tidal bundles. These are the sand layers which are bounded by the mud drapes. So that's a single tidal bundle. So just like in your tidal rhythmites, you can also get evidence of monthly neap spring cycles also preserved in crossbeds. Okay. So you get those tidal bundles where you get these layers of sand separated by mud layers, right? So in the raw record, sometimes let's say you get this crossbed here, is dipping towards the right. So the direction of dune migration is towards the right, and that is going to be the dominant tidal current. Okay. And then you look at the packages of tidal bundles, you get these thick packages of bundles here. Sorry, typo. This should be thick bundles. So it could be 14 to 15 packages or 7 to 8 packages, depending on whether it is semi-diurnal or diurnal, or whether it is semi-diurnal or just, sorry, let's clear my mind first. So because of neat spring tidal cycles, you can get thicker bundles developing during spring tides. Okay. thick sands with thin mud layers in between. And then you can get thin bundles, thick mud and thin sand in between, narrow package, developing during neat tidal cycles. And you can even count the number of bundles here, and they will correspond to your individual daily tidal cycles in the month. Okay, so you should get 14 to 15 uh, tidal bundles in your neat packages. In your neat package, if it's semi-diurnal, you get 7 to 8, or you only get deposition during dominant tidal currents, you also get 7 to 8, and get the same kind of roughly the same kind of number in your spring tidal package here. So you get this thick, thin, thick, thin alternating packages of tidal bundles, and this represents neat spring cyclicity. Neat lower energy, thinner, muddier packages, spring high energy because of a high tidal range, thicker, sandier packages in between. Okay, so you get alternating packages of thick bundles and thin bundles. Each needs spring cycle, semi-diurnal system, 14.7 days will produce 28 to 29 bundles in the crossbed. So example, this is from Sarawak, an outcrop here, and you can see this decimeter thick cross-bedded sandstone bed, and you can see the cross-bed faucets inside it, right? And the darker lines here represent mud drapes. And notice that the mud drapes are concentrated in packages on the right-hand side here and the left-hand side here. In the middle, you also have mud drapes. They are far in between. You have thicker sand in the middle. So this can be interpreted as deposits of a neat tidal cycle here, a spring tidal cycle here, and another neat cycle here. So this represents roughly 14 days of deposition. So evidence of neat spring cyclicity in outcrop. So in the previous facies that we've been looking at, well, all those three facies were developed because you have regular periodic deposition, right? During ebb and tidal current, and then intervening slackwater period. So you get interlayering between sand and mud. Okay. Now let's look at another kind of facies. This is herringbone crossbedding. So you have dunes, and inside the dunes you have internal stratification in the form of crossbeds. So remember, in the tidal system, you have two opposing currents. You have current reversal. Okay. So maybe originally you had one current moving from left to right. Let's say that is your ebb current. And later on during the day, the tidal currents move in the opposite direction. And that is your flood current. Right? So you get two crossbeds which are vertically adjacent, overlying each other, but the dip direction of the crossbed faucets are opposite each other. These beds here have crossbeds here dipping towards the right, here dipping towards the left. Okay. So this is herringbone cross bedding. If you find this, it's a relatively good indicator for tidal currents influencing deposition in the basin. So So you might even want to do a more quantitative study. Let's say you have a very thick succession of rock, lots of crossbeds, and you just measure the dip direction for each individual crossbed faucet. So you can plot a rose diagram for paleo current. Right? You've done a similar exercise at Bukit Tengku Lembu in Perlis during the sedimentology field trip, right? But this one, we're looking at the dip direction crossbed faucets. So in a tidal deposition setting, if you plot large numbers of crossbed dips, you start to get a bimodal paleocurrent orientation. So you get readings of crossbeds dipping towards the left here, towards the west, sorry, and then you have crossbeds which are dipping towards the east. in opposite directions from each other. So this can be interpreted to represent the two opposing tidal currents. And because you have more crossbed forces dipping towards the west, this might be interpreted as the dominant tidal current, and this is the subordinate tidal current direction. So if this was a 1 million year old rock succession, we can say that 1 million years ago, the tides were operating west to east in opposite directions here, right? Or another example here is the same here. In this case, you have symmetrical tides. Okay? You don't have one dominant current. Both are roughly the same magnitude, opposing north-south directed tidal currents. So evidence from bimodal paleocurrent directions. Another important characteristic is people have seen is that crossbeds in tidal deposits tend to be of the same thickness. Okay? So you might have a thick succession and you have lots of crossbeds at 10 centimeter thick. They are of relatively uniform thickness. All of them are roughly around 10 to 15 centimeters thick. So you start to think, most likely this was a tidal system because the position was regular. Remember, in a tidal setting, you get regular periodic deposition. And the other criteria is opposing current directions because of current reversals. So I think this is the best. This is a textbook example of herringbone crossbedding. This is from the Airport Road outcrop in Miri Town in Sarawak. It's mice in age. So you got these two beds here. These are both are cross beds, but the lower bed cross bed here has four sets which are dipping towards the left in this case, and then the overlying bed here has crossbeds which are dipping in the opposite direction. So this is herringbone crossbedding and interpreted as, these are interpreted as tidal deposits. Another outcrop of this is a really good outcrop in Bintulu, which we call it the Sungai Mas exposure, very near to the Bintulu Airport Sarawak. So this is a thick sandstone succession, part of a Nialau formation. It is Miocene in age. So we've logged the succession is up to 14 meters thick here. And if you look at the individual beds, they are made up of sandstones with crossbeds. And if you look at it bed by bed, you notice that the orientation of the crossbeds alternate from some of them are dipping towards the north-northwest, some of them are marked in black here, some of them are dipping towards the south-southeast. And this seems to be the dominant one because this has the highest frequency. So we interpret this as representing the two opposing tidal currents. And then you notice also that the thickness of the individual crossbeds are relatively uniform, about the same scale, decimeter thick. So that also supports tidal interpretation. Now we didn't do much in terms of paleocurrent measurements. It's a bit hard to measure the paleocurrents here, but a rose diagram made up of 9 readings here show you the two opposing directions, north-northwest and also south-southeast. So that we just this photo here shows only this part of the log section. Okay, so this is the final slide in my lecture today. So just to recap, just to summarize, you have rise and fall of the water level in oceans occurring on the Earth. And these rise and falls can result in lateral movement of water. So you get currents, right? So these are called tides. And tides form because of the interaction between the sun, the moon, and the earth. You get gravitational pull, and you get interplay with centrifugal forces, right? So you get regular periodic deposition of sediments because of tides. So most of the time it is in the form of sand, mud, interlayering. You get high energy sand deposition during the ebb or flood tides, and then you get intervening slackwater periods where you only get suspension fallout of clay and silt. Okay, so periodic fluctuations between sand and mud is a good indicator of tides, but it's better if you have other supporting evidence, and you can get supporting evidence from paleocurrent readings. If you have herringbone crossbeds, it shows you that there were current reversals, right? So you have two operating current directions, which might represent ebb and flood tides. So I'll just end here with this photo of a small exposure in the Nyala Formation in Sarawak, which have been interpreted as tidal deposits. Just look at why do we say it's tidal deposits? Well, first, you have heterolithic bedding, and these heterolithic beds can be very thick, can be up to 30 meters thick sometimes in the field. Okay, so you have alternating ebb flood currents depositing sand and slack water periods laying down mud drifts, which are thinner here, wavy bedding, elliptical bedding, even laser bedding. And then you also get thick, thin alternations of tidal bundles in your crossbands, which might represent neap spring cyclicity. But it would be nice if you could do some quantitative measurements here. And also evidence of bi-directional current orientations. We have herringbone crossbedding. The crossbeds here are dipping towards the left, the crossbeds below it are dipping towards the right. So the combination of these facies is more important when trying to interpret. The more evidence you have, the better. The combination of herringbone crossbeds together with mud draped tidal bundles in the crossbeds with evidence of thick thin alternating packages combined with thick intervals of wavy, lenticular, and phaser bedding. That combination evidence, to me, is strong support for tidal interpretation for the origin of these posits. And we can be very confident of the interpretation in this case because we take mudstone samples here from these localities here, and they contain fossils, including the pollen of mangroves. And from what you know of coastal systems today, mangroves occur only uh, along the coast. They are predominant in tidal deposition systems. Okay, so I'll end the lecture here. In the next lecture, we look at depositional elements in coastal systems. Okay, bye bye.